So thanks, everyone. It's wonderful to be back at Hope. It's been a few years. This is kind of an amazing speaking space. I just want to say, if I start acting weirdly, it's because all I can see are the reflections off the metal rims of the empty chairs. So I assume there are people in the room. Awesome. Maybe it's more comfortable if I assume there's not. Anyway. Oh, now I can see some blue people. Hello. So the title of my talk is Hacking Healthcare. I just want to start out by saying that I have more of a systems engineering perspective to healthcare. I'm a computer scientist by training. I'm interested in formal verification of systems. I got into healthcare by way of starting to try to build closed-loop systems to take better care of patients. So when I say hacking healthcare, I'm thinking of that whole system of healthcare, not medical devices particularly. I'm going to talk a little bit about hacking medical devices and where that is, and in my opinion, is not helpful a little bit later. Okay. That did not advance the slide. There we go. Okay, so two things really got me interested in healthcare, and I'm hoping my ulterior motive here is to get some of you interested and help you to get you to help solve some of these hard problems as well. So there's really two phrases that struck me when I started to work on medical devices back in about 2001. One was this idea of evidence-based medicine, which is a great idea. The idea is that you do clinical treatment, you treat patients based on scientific evidence of how effective those treatments are for those groups of patients. And I think this is a really good idea. The question that it begs is, what in the world were doctors doing before this? And the answer is kind of the same thing that they're doing now, treating based on what they're taught in medical school. And there's an old saying that half of what you learn in medical school is wrong. You just don't know which half. So you treat based on what you learned in school, what you see with the patients that you work with, and what you hear about, and what small fraction of the medical literature you as a practicing clinician are able to keep up with. So evidence-based medicine, the idea is that you do scientific studies and you see how effective treatments are and you change treatment based on that, is really difficult to do for a few reasons. One of them is that it's very difficult to collect enough data to do those studies, and I'm going to talk some about those challenges. The other thing that really hooked me on this space is the idea of preventable medical errors. I've got two pictures up there. One is the 1999 report, To Err is Human, in which the Institute of Medicine reported that 98,000 people just in the United States were dying from preventable medical errors each year. There's been several studies following up on that, a bunch of reports following up on it since 1999. The numbers keep doubling kind of each time they do another report. The second follow-up said, well, maybe it's 1 to 200,000, and the most recent number, and that leads to this headline of medical errors, the third leading cause of death, is 200 to 400,000 deaths per year from preventable medical errors. And so I want to dig into what kind of errors are we talking about, what do we mean by preventable, and what could we do to start preventing them, and how do we build better systems where it's either harder to make errors or where we can at least catch, document, compensate, and similarly to what aviation has been able to do, and a plane crash happens, you investigate the cause, and you try to roll out systems that make sure that cause doesn't happen again or doesn't result in another crash. So how could we build those kind of systems in healthcare? I also want to introduce the idea of a wicked problem, which being from Boston, I love this phrase. So a wicked problem is, and this is an eye chart for me to read even here, so I apologize, but it's the Wikipedia page and you can pull it up. It's a problem that's difficult or impossible to solve because it's tied up in all sorts of systematic issues. You can't fix it with a quick technical fix because there's social or workflow problems. You can't really dive into the workflow problems because you don't have the technical stuff to help support the solutions. And it's just these kind of tough, very difficult, almost intractable problems. And I think those are the kinds of problems that we face in healthcare. And that's why I'm interested to bring this talk to sort of this audience, is that I think as hackers, we're very used to working in spaces that combine these kind of social aspects with technical aspects and trying to affect change in very complicated systems that we can only influence sort of around the edges or in indirect ways. I think hackers bring that mindset of how do we make a minimal change in a system that gets it where we want to go without being able to say, well, I'm king of the world and you all have to do it this way now. I also want to introduce the term interoperability. I started working on medical devices in 2001, started working with the medical device plug-and-play interoperability program in about 2006. And when we started that program, my boss likes to say it was before the iPhone, and people didn't really know what apps or interoperability meant. So what we mean by interoperability is the ability to use the devices, the existing medical devices, as sensors and actuators in sort of a control theory sense. So we want to be able to read data from one device, process it, use it to control another device, and not really care whether our heart rate comes from a Philips brand monitor or a GE brand monitor or a pulse oximeter or an EKG, just that we have an accurate measure of heart rate. So some of the themes I want to get into. Clinical spaces are really complicated. There's a lot of actors. There's frequently misaligned incentives. What the patient wants may be different than what the doctor wants to do. What the insurance company wants as a good outcome from the healthcare system may not be what the patients want. And there are increasingly data brokers, data aggregators with their own sets of desires. Consumer and professional are becoming more blurred. We have patients who are getting more and more acute care at home, things that would have in the past happened in the hospital, patients on ventilators, on infusion pumps, getting dialysis and so on, in home spaces. Consumer devices are also becoming increasingly capable. It's not just heart rate from a Fitbit now. You have a lot more capable devices doing much more acute things. Care is becoming increasingly automated, and I'm going to try to make the argument that it's really about the data. A couple of pictures to sort of set the stage. I really hope to be able to use a laser pointer, but I don't think it's going to work. So on the right, we have a rack of infusion pumps. And this is not like a storage closet. These are 12 infusion pumps, 9 syringe and 3 large volume that are being used on a single patient. Just one caveat, these are pictures from the internet, not pictures of our clinical spaces. Imagine walking into a room with those 12 pumps and saying, well, the patient's crashing, stop the heparin. Well, which pump is it in? Where's the stop button? It's impossible to build an integrated dashboard for these kinds of systems now. Along this idea of the blurring of consumer and clinical worlds, I want to talk a little bit about those different worlds and what kind of applications we might want to build. So some of the common things that we try to build to improve healthcare systems are documentation, both through electronic healthcare records. So EHRs, electronic healthcare records, have been a really big topic. A lot of hospitals are spending a lot of money to install systems. I don't think those systems are going to be adequate to affect meaningful change and meaningful patient safety improvements. I think that the EHRs are great for billing, which is what they originally intended for. They are good for some kinds of documentation, but you don't get high enough resolution data, you don't get high enough quality data, and you don't get the data provenance that you really need to build applications to affect meaningful patient safety improvements. So we've got documentation. We have sort of health and wellness apps, and these are becoming more and more widespread, whether it's Google Health, Apple Health Kit, et cetera. Clinical decision support applications where it's taking some measurement, some physiological measurement, some other kind of measurement, maybe a short survey or something, and doing some kind of health treatment. And then finally, physiologic closed-loop control, which is kind of the most complicated. And that's where you have a closed loop where you're measuring a patient's vital sign or something about the patient, blood glucose, and using that to control something that's affecting the patient. So you're measuring blood glucose and you're controlling an insulin pump. We also have different user communities. So these are going to include people using systems at home, clinicians, researchers, but also stakeholders like insurance companies, device manufacturers, and these data aggregators that are sort of, I think, playing an increasing role. These, again, are kind of squishy categories, especially when you look at projects like the open source artificial pancreas groups that are hacking infusion pumps with homebrew control systems. They're kind of medical device manufacturers, but they're also not regulated as medical device manufacturers. They're not building under the same kind of quality system as medical device manufacturers, and they tend to often be the users of the systems as well. So we run the whole gamut from health and fitness kind of applications, weight loss, dealing with chronic conditions, in healthcare spaces, we're dealing more with patients bringing their own devices in or bringing their own data in and trying to integrate that into displays. If we have blood pressure measurements from a patient's visits to the hospital, but then we also have blood pressure measurements they're taking at home. Should we put those together in one dashboard, even though we know the hospital ones are taken with high-quality calibrated equipment and the home ones are taken with whatever the cheapest blood pressure cuff at CVS was? We're currently trying to solve these kinds of things in hospitals. And finally, we have researchers that might be doing a clinical study and providing devices to patients, or might be just aggregating data from that patients are volunteering. In that other category, I want to talk a little bit about data aggregators. I think that these are becoming increasingly important from a privacy and security perspective. And I would include there not just the companies that are manufacturing the home measurement devices. The manufacturers of blood glucose meters, of course, have the blood glucose data. And we'll question that, of course, a little bit in a next slide. But we also have places like Google or Apple or wherever you bought your phone from that have increasing amounts of data that is relevant to health, especially when we start looking at de-identification or re-identification of health data. If Google has your location information, then they may be able to re-identify a data set that's released by a hospital, even if that data set doesn't include any of the HIPAA-protected data elements. One of the things that we run into a lot in trying to build better health systems is this idea of scaling or of integrating data from multiple systems. So typical Internet of Things or home wellness devices, your Fitbits, your Omron blood pressure cuff from CVS, your glucose meter, your weight scale, all follow a similar kind of pattern. You have the device, it has some kind of link, often Bluetooth, to an app on a phone. That phone app then connects to the manufacturer's server. You can go to their website, log in with your credentials, and see a nice little graph, or maybe download a copy of your data. But there's typically not an API to communicate directly with the devices. And it's very rare at this point for there even to be an app to query the database in the manufacturer's cloud. So when we try to build an application that integrates data from multiple devices, that's very hard. And Apple and Google both have projects where they're trying to build fitness or health apps that are able to connect to these devices. But that's really by virtue of their size and weight, giving them more leverage with the device manufacturers to get APIs, to get connections in ways that people who aren't that big don't have. Okay, so we see some common kind of patterns with integration, and this gets to why it's difficult to gather data, why it's difficult to do these kind of clinical trials to support evidence-based medicine. So on the top left, I'm going to try this. I can't resist. It sort of works. Over here, we have this idea that we have an app that needs data from a few different devices. Maybe it's going to pull data from this patient monitor and from this capnograph and use it to control a ventilator. And a typical application or typical place you might want to do that is weaning a patient off of a ventilator in an ICU. Patients are on a ventilator in the ICU, maybe for several days. At some point, they're getting ready to come off the ventilator, and you go through a reasonably standardized algorithmic process to take them off the ventilator, of decreasing some of the settings, trying to see how they do without as much support, and eventually completely taking them off the ventilator. And if you're a clinician doing that, you can maybe go into the room and check once an hour, once every 15 minutes if you're really fast. If we have an algorithm doing that, of course, we can check many times a minute. So we think that we can do better patient care with these kinds of algorithms, even than a very attentive clinician can, once we're able to integrate the data. Another kind of architecture is this sort of cloud one that I alluded to with the home-based devices, where we have a blood pressure cuff that talks to the cloud, that talks to a app that the patient's able to run. Third architecture, the pattern that's very common in hospitals, is we have a fleet of devices from one manufacturer. Here we have a bunch of infusion pumps, and they communicate with that manufacturer's server, which is installed in the hospital's data center somewhere. So if you want data from any of these devices, the only way to get it is to go through that manufacturer's server, their API, and you get the data that they've chosen to provide. Last architecture that I want to point to is something that's sort of becoming more common in home fitness. And we'll dig into that a little bit on the next slide, where you have an application that's running locally that communicates with a bunch of devices and then communicates out with a larger application in the cloud. And this is the pattern that in our research group we've sort of followed with trying to implement a architecture for healthcare data integration. And I'll talk some more about that project in a second. But that architecture is, you have a bunch of sensors locally. Here we've got somebody on an exercise bike, and they have heart rate sensors, respiratory function sensors, blood glucose, blood lactate. Home fitness enthusiasts, freaks, whatever, are setting up their basements, and myself, I have to admit, included, setting up basements with more stuff than is in like a physiologic lab from a few years ago. You're really able to measure and monitor to a much higher degree than was previously possible, even in professional settings. And the equipment is becoming more and more inexpensive. Some of the reasons to do this are applications like Zwift, where you have multiplayer online environments where you've got several thousand people in their basements all around the world collaborating and competing in a virtual environment. So you're in your basement pedaling on your bike, you see an avatar of the bike, and you see everyone else's avatars, and you can race online. And the more equipment you have, the more vital signs you connect, sort of the more immersive it is, the more data you see back. So these home fitness things are not just, your weight scale, your blood pressure cuff, but are starting to get much more advanced. We even have a physiologic closed loop control here where we're measuring heart rate, and some of the other vital signs, and using that to control resistance of the trainer and so on. As we move more into acute care spaces in the hospital, I tried to map out sort of the space of what kind of applications we want to have. And I think there are two important axes here. Two most important are what's the time scale of the loop that you're trying to close with these. The other is how critical is this? And so we go from an optional kind of application like home fitness. If it doesn't work that day, you're not going to die. Weight management, if it doesn't, on the other end of the time scale, weight management is one of these where, again, if it doesn't work, you're not going to die. Up to life critical. So IABP is an intra-aortic balloon pump. There you have, you're measuring electrical activity from a malfunctioning, essentially, heart. You're using that electrical activity to coordinate inflation of a balloon that's inside the heart or in the aorta. And the timing has to be synchronized within a few milliseconds so that the inflation of the balloon supports the heart that's trying to beat. If it doesn't quite sync up, then you actually interfere with that heartbeat, reduce the amount of blood flow to the heart muscle itself, and you can lose more heart muscle very, very quickly. And so synchronizing within a few milliseconds is really critical there. So that goes up at the sort of extreme of very fast control loop, very life critical. Some of the other ones up there are defibrillator synchronization, infusion interlocks, we'll talk a little bit more about, and alarm systems. Things over on this end are automated ventilator weaning that I mentioned. It happens over a period of sort of hours to days, and if it doesn't work that time, you can go back, you can do a manual process, you can try again. Medication reminders, they're important, they're going to help people stay alive long term, but if you miss a day, it's probably not that critical, and there are other ways of remembering. So as we're trying to implement these, and we sort of go back to those architectures, we start looking at how do we actually build these in a real hospital? Because we can't typically just connect directly to each of the devices in a patient room. Either the devices don't have that interface, the manufacturers only provide data through a gateway server, or the ports may already be in use. That's something I run into quite commonly trying to build systems out in hospitals is, well, I'd love to connect to the serial port on this device, but it's already connected to something else. So there's limited connectivity, and you run into those kinds of limitations. So typical architecture for this is you've got some medical devices, and here's some patient monitors. This patient monitor's on this patient. This other one is on some other patient. You'd have, maybe up to a few hundred patient monitors on a single network. Those all communicate to a gateway server, and that gateway server then exports some data. A lot of the manufacturers want this device network to be really dedicated to their device, and they've done all of their safety analysis, they've done all their testing for FDA certification with the assumption that there's nothing else on their network. And so if you start trying to connect other things to the network, like applications for patient safety, you start getting nasty letters from the manufacturers saying, well, you've now messed with our network, and if there's any problems, the liability is all yours. So to avoid those nasty letters, we like to connect through the manufacturer's gateways when possible. That means that the data that we're getting from the devices is delayed by many hops. The semantics of the data are often kind of muddled because it goes through several layers of translation. We would often, for instance, connect a ventilator here through the patient monitor, which does some of its own averaging, drops some samples, changes names of some things. The gateways often also only allow a few simultaneous connections. So if we want to, I work at a 1,000-bed hospital. If we want to have 1,000 patients connected, we would need a lot of gateway servers. But this is kind of how we have to build things now. To get data from the monitor into the patient safety application, we have to go through these multiple steps, and I've greatly simplified the steps here. And then to get control back out from this application to an infusion pump that's going to infuse a drug to that patient, we then have to do those steps in reverse. So go through the gateway server, pass that command, pass it to the right device. And so you run into kind of the problems that you would expect with making sure that you've got the right device, that you're talking to the device that's actually connected to the patient you want, with having the right credentials, and with trying to buy and procure systems that even support these kinds of applications. I mentioned that I've simplified this. I'm just going to flash quickly. Here's our attempt to draw out what it actually looked like in one hospital. And this was to draw that same system of, if we want to have a patient monitor over here, here's our patient on the bed. We want to have a patient monitor here connected to an infusion pump that's over here somewhere. What steps would that actually have to go through? So, the silos are different servers, the lines represent different networks, and it all gets horribly, horribly complicated. And I think that we left out most of the hospital's firewalls, most of the segmentation, and the security appliances that are stuck in there as well. So the sort of logistical challenges to building these systems, I think, are quite high. We've had some success in doing it in more kind of constrained or limited circumstances. So like build a system, install it in one room. And in that one room, we're going to connect directly to the devices or connect directly to the server. And we've been able to build some things successfully that way. One of the things that makes engineering and healthcare, I think, different from other domains, one is that there's no real single system integrator. If you're building an airplane, if you're Boeing or you're Airbus or you're whoever else builds airplanes these days, you are the single system integrator. There's one place that can do all of the system testing, that can really check that the whole thing works. In healthcare, it tends to be the hospitals, and it tends to not be integrated at one time. Manufacturers will come in, they'll send their engineers to install individual subsystems, but there's no one really looking at that overall larger system of systems, other than potentially the hospital IT or biomed folks, who, by the way, often are not on great terms with each other. Probably one of the biggest fights that I started was saying, well, okay, we're going around, we're trying to get data off of devices. We're sticking little single board computers on the back of the devices, and we like to use BeagleBones, Raspberry Pis also work. We then have to connect Ethernet because wireless is hard and complicated. Ethernet just simplifies things greatly. So we then have to connect Ethernet. We also have to plug the thing into the wall somewhere. So why not use power over Ethernet? And the answer is that, well, power over Ethernet would mean that it's coming from the IT department from the switch in the server closet, that the power to the thing is coming from that. It's then connecting to a medical device, which has to be tested for electrical safety by biomedical engineering. And how is the biomedical engineering department going to do electrical safety testing on the network switches? And, just, it wasn't worth struggling through the layers of bureaucracy, honestly. We just plug the thing into the wall. Another difference between healthcare and other engineering disciplines, I think, is that we don't have a good plant model. Again, if you're building an airplane, you have good mathematical models for what it's going to do if you move the flaps all the way one direction or another. And these are all parameterized for how fast is it going, how dense is the air, et cetera. But you have a mathematical model for how the thing is going to behave, and that's pretty accurate. For patients, you really don't have that. We're starting to build some of those. Personalized medicine promises that we'll be able to build more in the future. Machine learning folks are promising that, well, once we have all the data, we'll be able to generate patient models. And what I mean by a patient model is a model of how a patient's going to react to a treatment. So say I have a person and we give them some pain medication. They've just had an operation, they're in the surgical ICU after a cardiac bypass surgery or something. We're going to give them some pain medication. I want to know if I give them this much morphine or fentanyl, how should I expect their heart rate and respiratory rate to change? And at what point does the heart rate and respiratory rate indicate that they've had too much? By the time that we've given them so much morphine that they stop breathing, it's a little late. We'd like to detect it before that. And so how do we make a patient model that says, well, for this patient, for this guy, for Alice or for Bob, how do we know that we've given them enough to control their pain, but not so much that we're going to make them stop breathing? And often this is done by using patient-controlled analgesia. And the sort of genius idea there is that rather than trying to predict, well, I'm going to need 10 milliliters of morphine and you're going to need 5 liters or whatever. Sorry, did I mention I'm not a medical doctor? So rather than trying to figure out how much people need, you sort of get a baseline of, well, a good single dose is this much. And if we program a lockout so you don't get more than 4 doses per hour or whatever, you're probably going to be fine. And then give the person a button to press. And you press the button, you get a dose of medication. And I think most people at this point have either been in the hospital and had this or visited someone and seen it. But the idea is you've got a button to press. And if you want more medication, you press the button. If the pain isn't that bad and the medication makes you feel nauseous, then don't press the button, until you need to. And the sort of fail-safe aspect to it is that if you've gotten enough morphine that you fall asleep or are knocked out, you can't press the button. So it's fail-safe. Where that breaks down is if the single dose is so large that you get an overdose from one, or if we see what we call PCA by proxy, where someone else is pressing the button for you. And this is commonly used for folks who, for whatever reason, aren't able to handle pressing the button themselves. Maybe because it's a kid, maybe because it's somebody who's just not comfortable doing it. But you end up with a family member or caregiver pressing the button for them and potentially triggering an overdose. So despite it being, in concept, kind of a fail-safe system, we still see overdoses way too often. There's a engineer at Baxter, one of the infusion pump companies, did an analysis a couple of years ago of the FDA's MAUDE database, where they track all kinds of problems with medical devices, and found that there's probably a handful of deaths or serious injuries from PCA overdoses per day in the U.S. So we're interested in building these kind of models and saying, well, how do we build a better alarm system? How do we detect that a patient's getting an overdose and then either just sound an alarm or ideally stop the infusion pump? And the first thing that we need to do is build a mathematical model of how we expect them to react to getting this dose, and then start to define some of these spaces where we say, well, if the vital signs are in this area, then they're kind of safe. If they're in this area, then we should sound an alarm. And if they're out here, then the patient's in serious trouble. And what we want to do is sort of track the patient's progress through this state space. When they get into this alarming area, then trigger quickly, but write our model in such a way that the time that it takes for a patient to go from here out into critical is long enough that we're pretty confident that we can get somebody into the room to fix things and stop a pump. Fortunately, humans are slow. Reaction to medication typically takes minutes, if not hours, and computers are pretty fast. So we can do quite a lot in the time that it takes for somebody to react to a medication, and we can catch things pretty early. What we're missing to do this sort of at scale is really large data sets gathered from many patients. Overdoses happen, like I said, a handful of times a day, but there are tens of thousands of infusions per day, most of which aren't documented in any kind of automated or detailed way. So building a data set of what it looks like when somebody gets an overdose is really hard. And that's true for not just for that PCA use case, but for most use cases where there's a medical error or an accident or an unexpected reaction to treatment. These really take either very large clinical studies or automating data capture and recording kind of for everyone. So the solution that I've been involved in trying to build is called OpenICE. ICE is the ASTM 276109 standard, re-ratified in 2013 and back up again this year. It happens every 4 or 5 years. And OpenICE is our implementation of that. ICE there standing for the Integrated Clinical Environment, not either William Gibson's ICE or the ICE that we all love and will hopefully not have to love for too much longer. Anyway, staying out of politics mostly. What ICE includes in the architecture here is it's actually pretty similar to that cycling, that Zwift kind of architecture. We do some local control, and then we also talk to external systems to pull in lab data, vital signs records, communicate stuff back to the medical record system. So our local control happens through, I'll just step through it. We've got a patient here on the bottom. We've got the caregiver on the top. So from that you can surmise that this was mostly written by clinicians and not by patient advocates. But, which is a slightly serious comment because I'm involved in a lot of these standards, and we tend to have mostly folks from device manufacturers involved in writing medical standards and medical IT standards. Maybe a few clinicians and almost no patient advocates. So if you're interested in getting involved, please do. So we've got our patient, our caregiver. We have an ICE supervisor, which runs the application, or a set of applications. You may run many simultaneously. We have a network. We have a set of adapters to devices. We might have a device that speaks directly, that uses our interoperable protocol and speaks directly. And then we've got a data logger hung off here. And the data logger, I think, is pretty critical. The idea is similar to a black box recorder on an airplane. We want to have a independent in the sense that it's not tied to any single device or device manufacturer, and standards-based in that the data should be written in a common terminology, record of what happens to a patient, and recording that by recording the electronic outputs of the various devices and having a record of what commands get set to what devices. It's really, really common when there's a problem with a medical device or a system to see the various vendors who are involved just all point fingers at each other, and it takes years to clean up. I've seen this with infusion pump systems where half of the infusion pumps are connecting to their server and database, the other half aren't showing up at all, and it turns into a multi-year fight between the vendor who sold the wireless system and the vendor of the pumps and the company that did all the installation. So we want the data logger so that we have an independent record. We can, if I'm talking to the manufacturers, I say, so that we can prove that that it's not your fault. To the clinicians, it's more to identify what happened. It's not uncommon now if someone passes away in the hospital. Someone may go into the room and find that they've passed, they're dead in their bed, and What happened? Well, you sort of surmise from the medical record. If they were, if it's not an unexpected occurrence, you assume that what you expected to happen happened. If it is unexpected, then you can try to quarantine the devices. You can try to grab all of the medical devices before they get reassigned to another patient and wiped. And there are, quality improvement and essentially forensics groups in most hospitals that will try to dig through and figure out what actually happened. But there's no standardized data format within the device. There's no standards for how they log data. And so it can be very difficult and very, very time consuming to go through and try to coordinate these logs. The devices in most hospitals aren't time synchronized even. We did a study a few years back where we flew a biomedical engineer around to 5 different hospitals, recorded the clock time on, it was about 2,000 medical devices, and tried to see how far off they were. My favorite device thought it was January 1st, 1970. But it was really, really common to see devices that were 15 minutes to a few hours off. If you regard accurate as within 5 seconds, then 4 or 5% of the devices were accurate. And so this makes it really hard to determine even basic causality. Did the patient's heart rate go up after they got the antibiotic and maybe they were allergic to the antibiotic, or did their heart rate go up and then later they got the antibiotic and it's unrelated? It makes it really hard to go through and do any kind of root cause analysis if you can't trust the clocks on the individual devices. Okay, so our implementation basically follows that architecture. The picture is a build in our lab, or our old lab. The architecture looks kind of like this. We tend to connect to individual medical devices using something like a beagle bone. Beagle bones for a couple of reasons. One is we can plug a serial port right into it in a way that's a little more complicated with like a Raspberry Pi. Also, beagle bones, we were able, through one supplier, to get a huge number of these really anonymous-looking black metal boxes. And if it's in an anonymous-looking black metal box and we stick it on the back of a medical device, then nobody looks at it twice. If it's a Raspberry Pi and it's in a clear acrylic case and you can see all the blinking lights, then people want to know what it is and they ask questions about it. So the beagle bones have worked out well for us. We also got some in orange boxes that we used for the data logger so that it looked more like an aircraft black box. But the anonymous black box has a great deal of power. So we use those to translate from the proprietary mostly serial protocols of the devices. There's both a proprietary data communications protocol and then usually a proprietary data representation. They have their own terminology set. And we try to map that to a common way of moving the data around. We tend to use a publish-subscribe middleware. We like DDS for this implementation. I'm happy to dive into more detail about why we picked it or what the advantages and disadvantages are. But our current implementation that's on GitHub uses DDS. We use that bus to share data around, and we hang applications off of there. So a device says, hey, I've got heart rate data for Bob. The application says, I want Bob's heart rate data, and the middleware takes care of matching those up. We also have some data export that we do through Node. We have some data recording that we built a few years ago, and so of course we used Mongo. And we connect to external networks that we can export data as well. I had a placeholder for an OpenICE demo, which I'm not going to do, both for sort of lack of time, but also because when I tested it before I plugged my laptop in, it wasn't working. So sorry for that. You can go to our website, openice.info. Openice.com and .org are hockey sites. I think .net is as well. So we got .info. And if you download the code and run it, you see something like this. So this is our ICE supervisor. We have a set of connected devices. We have a set of applications we can run that includes some data visualization. Because data visualization ends up being really, really hard to do in a hospital because you can't get the data from the devices and put it all in one place. And so it ends up being very difficult, very complicated. And when you can get all the data from the devices, it's often so old that you can't really do a real-time dashboard. So we built this as a way of illustrating what we could do if we had high speed, high fidelity, standardized data from the devices. What kind of applications can you build? And so there's examples of auto-validation, where we can push data into a healthcare record and automatically validate it by correlating either multiple sources of the same data or using more advanced kind of algorithms. Say, yes, this looks real, or no, this is not real. There is a problem with medical data where a lot of it is really, really noisy, and a lot of it ends up being inaccurate. So you have data from pulse oximeters that go on a fingertip, and you get a heart rate, and you get a blood oxygen saturation number from that. But if you're squeezing a phone, if you're pushing your arm up on the bed rail, if you have a blood pressure cuff inflating on that arm, if you're talking on the phone and agitated, you can start to see just wrong numbers out of these things. It's one of their failure modes. Most of the devices have similar kind of failure modes, where in everyday practice, you commonly see either erroneous data or drops of data. And so this gives us a platform where we can sort of compare multiple sources if we have multiple devices connected and filter out some of that. That erroneous data is one of the things that's really led to a problem in false positive alarms in hospitals. And by false positive, I don't mean that the device shouldn't be alarming. It sees something that the manufacturer has identified as a reason to alarm. Maybe the finger clip has fallen off and you're not getting a heart rate measurement at all. And as far as that device knows, the patient's heart might have just stopped, and it should scream as loudly as it can and get a clinician to run in. But the effect of deploying that at scale is that you've got a bunch of pulse oximeters in the hospital that are screaming all the time, and you get nurses having alarm fatigue where they can't respond to all of these, or they can respond to them, but they spend a huge amount of time doing so, and it really takes time away that they could be spending on patient care. So I think better alarm systems are one of the first areas that we really need to address, and that's something that we've tried to build and prototype through this system. I'm going to go back slightly. This is cool, but I'm going to skip it. Sorry. So one of the sort of key questions we run into is we start talking about data aggregation, data collection, whether it's to feed smarter alarm systems or for machine learning or for other kind of data analytics, is can we even combine device data? So I've drawn 3 different patient monitors, and we've got 3 devices there. We have 3 slightly different definitions of vital signs. Each manufacturer gets to decide what they mean by heart rate, and maybe they're measuring it from a different part of the heart rate of the EKG waveform. Maybe they're averaging it over a different time period. Maybe they're processing it in different ways, and they probably are doing very different things when the signal is very noisy. And so you can end up with different definitions of these vital signs, even for something as seemingly basic as heart rate. And so one of the sort of key questions I have is, as we start to aggregate data and try to do machine learning on it, try to use those data sets to diagnose patients, are we going to be diagnosing real things in real patients, or are we just identifying with different ways that the device's signal processing algorithms have sort of colored or shifted the data? So how do we make data sets that are meaningful and useful, either for machine learning or for manual analysis or other kinds of algorithms? One of the sort of key things for a medical device is its intended use. And this is a sort of a technical term of art to FDA, that the manufacturer gets to specify what the device is for. So an infusion pump is for pushing a medication into a patient. A monitoring device is for measuring a particular vital sign, and they're defined for a patient population, a particular place, and a particular use. And one of the things that we really need is for device manufacturers to build devices that are intended to send data to other systems. We've seen some movement from FDA in the last couple of years on this. There's a new guidance on interoperability that says that this is a good idea and people should do it. It's a first step. But the difference between a clinical grade device, your Masimo or Nellcor pulse oximeter, and a cheapo that you bought off of Alibaba or wherever, is the metadata. It's the accuracy. It's how trustworthy is this data. And if we can start to annotate device data with that metadata, with a little bit more provenance information, then applications can choose whether or not to use that data based on that metadata. I just want to mention really quickly patient privacy and informed consent. There's this idea of informed consent, that if a patient is agreeing to allow their data to be used, they should understand those uses and understand where the data is going and who's going to use it. As those uses become more complicated, this has, I think, gotten a lot harder. And so I would just say one of the big open questions is how do we explain to data how do we explain to patients how their data will be used? And how do we obtain, track, and I think retract permission? I don't have answers for this. It's something we've been exploring. I'd be really interested to talk with folks who are working in that area. There are a lot of security challenges around the device interfaces and individual devices and around these larger systems. I would point, one of the critical ones, I think, is this idea of time management and timestamps. If you can't trust the time and the data, then it's almost useless. I'd also include patient consent under that. When we start looking at large-scale patient data sharing especially. Authentication and authorization of devices. When we connect a device to the network, we'd like to know, where did that device come from? Is it supposed to be in the hospital? A key thing that we need for that is a unique device identifier. And FDA has been pushing UDIs for devices for a number of years. They've been pushing it as a labeling thing. So your box of tongue depressors will have a machine-readable barcode that identifies the manufacturer. And that's great, and we need that. But when I talk about electronic UDI, I don't just want a machine-readable barcode. I want the device on its serial port or on its Ethernet port to spit out something that's ultimately traceable. MAC address only gets you so far. And then testing, verification, certification of devices. Talk a little bit more about that, particularly around patching. Devices are patched all the time, or at least should be patched all the time. One of the problems is that installing patches may break other things. And different hospitals, I think that all of this has been published pretty widely, but for instance, patching your Cisco router may break something in a medical application. So how do we ensure that the patches, when you install a patch, that it actually fixes what it's supposed to, but then also that the complex system is going to keep working when you patch that one piece without either taking too long, because patching can be a quite lengthy process. I've heard of one lately where it took half an hour to an hour to patch a central station. It's the computer that sits in the middle of the nursing station on a floor and shows all the vital signs from all the patients. And it's really not acceptable to take it down for an hour, once every couple months to patch it. So how do we do this without it taking too long, costing too much? I've also heard a lot about security from device manufacturers in ways that kind of makes me nervous. There tend to be two reactions from manufacturers to security concerns. One is to say that, well, the only secure device is one that you never take out of the box or that is never connected to a network. And I think that's on one of the first pages of the Orange Book, shows like a computer in a vault, and that's that model. The other is that, well, we're going to encrypt everything so that only our devices can read the data. And my response is that preventable medical errors kill a lot of people already, and that a lot of these preventable or even unpreventable errors are treatable or fixable if you have better connectivity, if you have the ability to build these applications, if you have accurate time-synchronized data, the ability to build these better apps. And that we need open standards-based interfaces, not proprietary encryption that means that only GE can read data on a GE network, and that turning off the communications will actually kill a lot of patients. Okay, so what do we want? What I would like is better patient monitoring, ability to build smart alarm systems, to deploy algorithms and analytics more widely. And what we're really fighting against is, to some extent, existing workflows where it can be very difficult to change how clinicians do things, often because the way that they've done things has been optimized over a really long period of time to avoid killing people, ultimately. They say, well, we tried it this way, and these bad things happened. So we changed it so those bad things no longer happened. And then you iterate a few times. So you keep changing the process, bad things keep happening, you keep changing it slightly to avoid that bad thing. Then it gets to a point where bad things don't happen too much and you're afraid to change it because you don't want to go back to any of the things that were happening. And the problem is that you end up sort of backed into a local maxima, where if you could change everything, you could really improve safety, but you're kind of stuck, and it's very difficult to change things too much. We see clinical spaces with a lot of actors, sometimes with misaligned incentives. The device manufacturer that wants their system to be vertically integrated because then they can sell more devices, they've got more lock-in from their customers, they make more profits ultimately. We see consumer and professional spaces getting more blurred, acute care devices, things that were only used in hospitals being used more at home devices coming into hospitals, and we're seeing more automation of care. And in my opinion, to really radically improve these systems, we desperately need more data from the devices, we need more data about patients, and we need better systems that allow us to track what's happening and really realize those promises of evidence-based medicine. Okay. But I think we've got a few minutes left for questions. Invite them. Thanks. Though I will mention, I can't see anything, so if you want to ask a question.
So far I'm the only person lined up, and I have several small questions. How often do you see reasonable patch infrastructures for applying patches with cryptographically signed updates by the manufacturer with key material in the device?
Sometimes.
Sometimes.
We actually do.
Okay.
No, seriously, we actually do from some manufacturers.
It's not a requirement,
by
though.
manufacturer. And I'd say that I think 5 years ago that was really rare. Maybe you got a disc in the mail from a manufacturer, and it's becoming much more common.
And similarly, how often do you see backdoors for installers or engineers that are documented, with default or unchangeable passwords in these devices?
Well, I don't think the manufacturers like to call them backdoors.
Yeah, but I do.
I bought a system for our lab once and really wanted to install and use it, and ended up having to do all the installation and configuration myself, despite spending 5 figures on support to do exactly that, because I refused to install the extra router, switch, and connection to the internet that they demanded to let their engineers log in. We are having more success with manufacturers and forcing them to log in through systems that let us track the individual who's logging in. And separating out, having more segmented networks and really trying to separate out those backdoors. But ultimately, I think that there are compelling reasons to allow a manufacturer to remote into a system in some cases. Not usually into the bedside devices. I'd say probably not ever into the bedside devices, but into the data aggregation systems, into the gateways, into the sort of management systems.
Hi. So in regards to security, which type of security do you see more of a concern with? Is it more of the real-time systems, or is it more of the patient data that would be a bigger concern from a security perspective, and where you've seen security vulnerabilities in particular?
So I will mention, I don't work so much on day-to-day operations.
Right.
With that perspective, my concern is much more on the patient data, frankly, at this point. I think that's the piece that we're seeing that has the most value to malicious folks, and that's where we're really seeing vulnerabilities. So far, vulnerabilities in medical devices have mostly been in the computer systems that are around them. So you hear, well, an MRI machine, got infected with WannaCry, and what it is the old Windows machine that's used to program to control to export data from the MRI machine, not the real-time embedded operating system, which is bad, but at least it's not, 10,000 infusion pumps each with a ransomware message.
Quick question on the applications you've deployed for the OpenICE platform. Have you ever implemented anywhere outside of hospital or larger healthcare systems, kind of with the advent of value-based care pushing to other modalities, other locations of service? So a multi-specialty group, an oncology treatment center, something outside of kind of the infrastructure required to support this?
Yeah, so that's really the dream. One of my motivations in doing this work is I think that As we start to have automated care, I think that in some circumstances, patient monitoring, alarms, some kind of, titrating drugs to effect, that kind of stuff, I think algorithms can do a better job than people. You obviously still need human clinicians, you need people to set this up. There are lots of things that the algorithms are nowhere near ready to handle, but there are niches where the algorithms can do a better job. We're seeing some automated systems being deployed in those kind of settings, like for conscious sedation for some kinds of procedures. There's commercial systems now that do that. For our implementation, some times that it's picked up and used by folks we know about because they get in touch. It's a BSD 2-clause license at this point. We know that it's been picked up by a couple of companies to build into commercial products, and that's great. We want them to do that. There's no requirement that they tell us what they're doing. So we don't know everywhere that it's ended up, but it has been used for better alarm systems, I think mostly in acute care settings, mostly in hospital settings.
Okay, thank you.
Yeah.
So I work in the optical industry, so I guess it's a little different in that no one is going to die from the type of things we're doing. To speak to his comment, I can tell you one of the more popular software packages has the name of the support company that is the vendor and a 7-character password baked in that can't be changed. And related to what you said earlier about the MRI machine, I'm dealing with $200,000 cameras that a small practice doesn't want to change out, but it's paired to an app that only works in Windows XP and needs an old version of Java. How do we hold these manufacturers accountable for having software that has to be so out of date to work with the device that's still perfectly functional?
Right, and so I'm really interested in industrial control systems. My other talk on Sunday is about manufacturing micro-electrical mechanical systems in your basement, and so I'm running Windows 98 there because that's what my mass spec needs. So I feel your pain. I guess to further complicate it, the medical device world is one where companies get bought, sold, change hands very, very often. And so even a company like GE, not to pick on anyone, but even a company like GE, a lot of their products with their logo on it are things that were built by another company, maybe a long time ago, that they acquired and have sort of pulled into their portfolio. And so they have interoperability problems of their own within their own company. I think that's true of most of the large companies. So we would love to see more support for older systems, updated computers to run the older hardware, but the usual answer is, I think, is probably the same in your industry, where the company says, well, no, we built that 20 years ago. The new stuff is so much better, and what you really need to do is buy a new system. What we end up doing in practice is, and this is for the older systems, it's also for most of the medical devices, is saying that these devices are either known to be insecure or not known to be secure. Nothing's known to be secure, right? So what we're going to do is segment them, firewall them, do as much intrusion detection as we can, and try to really keep them locked off and separated so that it's as difficult as possible. There are as many safeguards as possible to keep the devices from being accessed and saying that, well, maybe you can go on Bing and you can find a manual with that secret password, but you can't actually get to the device to type it in. Yep. Okay.